Good morning and welcome back. So today I would like to discuss the sequential circuits with reference to timing. So with reference to timing, the sequential circuits can operate in two different modes. Those are synchronous mode of operation and asynchronous mode of operation. So basically what is meant by synchronous and asynchronous means, in synchronous case, the signal means that a signal is clock signal. The clock signal is connected to all the elements simultaneously. That means applied. Okay, the clock signal is applied to all elements of the digital circuit simultaneously. For example, if you take a register, the register is a group of flip-flops. Okay, that is, each flip-flop is considered as an element in that register. So all those flip-flop elements can be driven by the clock signal simultaneously. That is, the clock signal is applied to all the flip-flops simultaneously. Okay. In case of asynchronous operation, it is not like that. The clock signal is applied to different elements in different timings. Okay, so that is the difference between synchronous and asynchronous operation. Now coming to VHDL representation of synchronous operation is, so in VHDL case, whatever the number of assignments, number of assignments or number of events happen, those are all with reference to clock, signal that is represented in the behavioral model using process statement, that too using clock as a sensitive input. Whatever the operations under the process, their execution depends on when the clock signal is changed its event. Okay, that is, when there is a change happen in the clock signal properly, then only the statements which are there in the process can be executed. Okay, so that is so see, here is one program. Okay, but this program is not with reference to synchronous. Let us see the previous program. Already we have seen the sequence detector case. In previous session, we observed the program is, see here, process of clock. Within the clock there is a if statement, many assignment statements with reference to when x is 0 and when x is 1. Okay, so like that many operations are there within the process, but all these operations can be taken place with reference to the clock. When the event happen in the clock signal, after that too, if the event is a rising edge, then only these operations can be executed. Okay, so that is, here all these operations can be done when the clock signal changes its state. Okay, so this type of action is referred as synchronous operation. But in asynchronous case, are not like that. Under the architecture, some operations with reference to some signal and some operations with reference to some other signal. So see, observe here. Here are two processes. One process having the clock as a sensitive signal or sensitive input, and another process having Q as a sensitive signal. Okay, that is, here two statements are there, Q equal to naught of Q and Y equal to naught of Y. But not both the assignments or the statements are not aligned with the clock signal. The Q is not Q, is the event, or this is the statement executed when an event occur in the clock signal. Okay, but not Y equal to not Y. Okay, this is y equal to not y is not synchronized with the clock signal. Okay, it is with reference to q. When there is a event happen in q, then only this statement y equal to not y will be executed. Okay, that is one statement is that is not both the statements with the same clock signal. Okay, so q is not of q is with reference to clock signal, whereas y is not of y with reference to q. Okay, so this is the example for the asynchronous operation. Okay, so sometimes you need to go for synchronous operations, and sometime you need to go for asynchronous operation. Compared to synchronous case, the asynchronous designs are very difficult, whereas synchronous operations are very easy, and you can easily implement the synchronous operations. Okay, then coming to, so next one is shift registers. Next topic of the sequential circuit is shift register. Okay, so basically what is register? So register means it consists group of flip-flops. Register is a group of flip-flops which is used to store more than one bit binary value. Usually the register is used. It includes all elements of the flip-flops, right? Now on these shift registers in the digital circuits, different operations can be performed. Those are right shifting, left shifting, right shift and circulate, left shift and circulate, like that. So based on those operations, the shift registers are categorized as four types: serial in, serial out shift register, serial in, serial out shift register. All these shift registers can be classified as four categories: serial in, serial out shift register, serial in, parallel out shift register, parallel in, serial out shift register, parallel in, parallel out shift register. Okay, whatever the operation, whether right shifting, left shifting, right shift circuit, left shift circuit, whatever the shift operation. Okay, so usually those operations can be done on registers, hence named as shift registers. But these shift registers are four types of we have. Those are serial in, serial out, serial in, parallel out, parallel in, serial out, serial in, parallel in, parallel out. Okay, what does the meaning of serial in, serial out, serial in, parallel out, like that? That is, the data enter into the register and the data extracted from the register. Based on that, these are the four categories. First of all, if you take the first model, serial in, serial out, that means here only one bit can be placed per clock within the register, and similarly one bit we can extract from the register per a clock signal. For every clock pulse, only one bit is loaded into the register or one bit extracted from the register. That is the meaning of the serial in, serial out. Similarly, if you go for serial in, parallel out case, serial in means for each clock pulse only one bit is we can place in the register, whereas while extracting per clock pulse, for only one clock pulse, all the bits of the register can be extracted. Only one clock pulse is enough to extract all the bits of the register. Similarly, parallel in, serial out means parallel in, that means all the input bits can be put in the register simultaneously. That is, only one clock signal is enough to place all the bits into the register. But while extracting, only one bit you can extract for every clock pulse. That is the meaning of serial in, serial out. Whereas in case of parallel in, parallel out, only one clock pulse is enough to place all the bits into the register. Similarly, one clock pulse is enough to extract all the bits from the register. That is the parallel in, parallel out operation. Now let us see the structures of each and every one. First of all, okay, this is the example for the register, which includes D flip-flops. How many D flip-flops here? 4 D flip-flops. This register consists 4 D flip-flops. All the D flip-flops driven by the single clock signal. So this is the asynchronous synchronous sequential circuit, and the data can be put into the register from the left hand side D flip-flop. You can observe it. X is the input connected to the register, whereas the output is collected from the extreme right D flip-flop. From the figure you can observe that it is Y. Okay, so Y is the output, X is the input. Okay, so serially one bit can be placed into the register through X. Similarly, one bit from the register can be extracted through the output Y. So this is a serial in, serial out operation. So based on with reference to this serial in, serial out, we can write the equations for the X, Y and also the outputs of each D flip-flop like this. So here N means present state, N plus 1 means next state. N is the present state, N plus 1 is the next state. With reference to that diagram, with reference to above diagram, output Y equal to Q naught of N, that is the present state of Q naught of N. Q naught is the output of the last flip-flop, output of the last flip-flop. This is the Q naught, this is the Q naught, Q1, Q2, Q3, like that. N number of flip-flops or N minus 1 number of flip-flops. This register, let us assume it consists. Therefore, Y equal to Q of N. Y equal to Q of N. Similarly, what is the next state of this Q0 of N plus 1? Q0 of N plus 1, that is the next state of the last flip-flop is the present state of the next higher level flip-flop, that is Q1 of N. Like that, if you write the equations for each and every flip-flop next state from Q0 to Qn minus 1, the equations can be expressed like this. Y equal to Q0 of N, Q0 of N plus 1 equal to Q1 of N. Similarly, Q1 of N plus 1 is Q2 of N. Like that, for N minus 1 number of flip-flops, what is the next state equation or next state value? That is represented through this Boolean equation representation. Okay, so all these equations represents the next states of the flip-flops. Okay, similarly, this is in general. If you observe, it is a right shift operation. Right shift operation. In right shift operation case, this type of equations you can observe. Suppose if you take left shift operation, if you take the left shift operation on same serial in, serial out type of shift register, left shift. Okay, in left shift case, Y is the input, X is the output. Okay, so in left shift case, so Y equal to Qn minus 1 of N, that is the present state. If you observe here, this is not only left shift and also circulate. So Y is Qn minus 1 of N. Okay, that is the output of the most significant D flip-flop, that is Qn minus 1 of N. And what is the next state of Qn minus 1 of N plus 1 is Qn minus 2 of N. Like that, if you go for LSB D flip-flop, Q naught of N plus 1 is equal to x. Okay, so like that you can express the values, or you can express the Boolean equations at the output of each and every flip-flop. Okay, so here we can observe both right shift operation and also left shift operation. Okay, then in the next class you can see what is the VHDL representation for each and every shift operation or the shift register case, right? Thank you.